Welcome to Deep Learning with PyTorch 0 to GANs. We are on lesson 3 today, Feedforward Neural Networks and GPUs. My name is Aakash and I am your instructor. By the end of this course, you will learn how to train generative adversarial networks that go from producing random noise like this to fairly good images of handwritten digits and anime faces. And you'll learn a lot about deep neural networks and the PyTorch framework along the way. You can earn a certificate of accomplishment by completing some assignments and building a real-world project as a part of this course. So let's get started. You can go to the course page 0togans.com. On the course page, you can enroll for the course and you can check out the previous lessons. So you have lesson 1, lesson 2, and the previous assignments 1 and 2. Today we are looking at lesson 3. So let's open up lesson 3, training deep neural networks on a GPU. Now you can catch a recording of this lesson here. And these are the resources we will be using today. So we will be using the notebook, training deep neural networks on a GPU. Let me open up this notebook. Now during the lesson or afterwards, if you have any questions, you can ask questions and get help on the community discussion forum. Just open up this thread and click the reply button here to post your question, and somebody from the community or the team will help you out. So let's open up training deep neural networks on a GPU. This is a Jupyter notebook hosted on Jovian, the platform we've been using to share all the material with you. Today we are on part 4, and previously we've looked at PyTorch basics, tensors and gradients. We've looked at gradient descent and linear regression, and we've looked at how to work with images and train an image classification model using logistic regression. So you can look through these notebooks if you want to get a sense of what we've covered so far and review the code. Now we are on training deep neural networks on a GPU. The first thing we need to do is to run the code. Now what you're looking at here, this is a Jupyter notebook and there is some code here. There are some explanations here, but this is a read-only view. To run the code, you can follow the instructions here. Now the first option is to run this code using free online resources, which we recommend if you're just getting started, but you can also run it on your computer locally. So we are going to go up, click on the run button and select run on Colab. And here you can connect your Google account and run this Jupyter notebook on Google Colab, an online platform for running Jupyter notebooks backed by Google's cloud infrastructure. So here we have it. We have the same notebook running here. Now one thing you might want to do first is to go to the edit menu and select the last option here, clear all outputs. What this does is this removes all the outputs from the code so that we can execute the code and see the outputs for ourselves. And today, since we are going to train neural networks on a GPU, and GPU is a specialized hardware, it's also known as a graphics processing unit or a graphics card. And graphics cards are very well suited for performing a lot of matrix multiplications and floating point operations very efficiently, which makes it easier to train neural networks faster. So neural networks that take hours to train on a CPU can be trained on a GPU in minutes, and we'll see why that is. But to use a GPU, you will need to enable it on the platform wherever you're running this notebook. Now on Google Colab, the way to do that is to go to runtime and select change runtime type. And here select the hardware accelerator as GPU. If you have hardware accelerator selected to none or TPU, then you will not be able to use a GPU. So please make sure you select GPU here. And once you do that, your runtime will restart. So let's get started then. We will run the first cell here. Now make sure to run the first cell. This is simply an integration to make sure that this notebook that you're editing here, it can be sent back to your Jovian profile. Now once you run it, you will see that the server initializes, and it will take a minute or two for the first cell to run because it will initialize Python. It will connect it to this notebook and it will download the required libraries here that we have included. But now the first cell is executed and we can move ahead. Now these are the instructions for Google Colab, where you can go to runtime and change runtime type to select your GPU. Otherwise, you can also use Kaggle, and there are different settings there to enable the GPU. On Binder, you do not have a GPU, and if you are using your own computer to run this code, if you're running Linux or Windows and you have an NVIDIA GPU connected to your computer, so this is typically part of your hardware configuration, then you can install the NVIDIA CUDA drivers and use the GPU for training PyTorch models as well. On macOS, you do not have the option because macOS is not compatible with NVIDIA GPUs. Now, all that said, even if you do not have access to GPUs or aren't sure what they are, don't worry, you can still execute all the code in this tutorial just fine without a GPU. Okay, so in the previous tutorial, and you can check out the link here in this notebook or on the course page, we trained a logistic regression model to identify handwritten digits from the MNIST dataset. So this is some samples from the MNIST dataset. You can see here that you have images. These are small images of handwritten digits. And the goal is to identify what each image represents, which digit each image represents. So the dataset consisted of 28 by 28 pixels of grayscale images of handwritten digits, and it also contained labels for each image indicating which digit it represents. Now we trained a model and we noticed that we were able to get to about 85–86% accuracy, but it was quite challenging to improve the accuracy of logistic regression beyond 87%. And this is because the model assumes a linear relationship between pixel intensities and image labels. And we'll review that soon. So today we will try and improve upon it using a feed-forward neural network. So today we are taking our first real steps into deep learning by training a real deep learning model. And this model will be able to capture non-linear relationships between the inputs and targets, and we'll see how. So first, let's begin by installing and importing the required libraries and modules. Now, Google Colab already comes with all the libraries installed that you need, so you do not need to run this cell. But if you are on one of these other platforms, you will need to uncomment the specific command here and then run that command to install the required libraries. Now let's get started here. We are importing a bunch of things that we are going to use. So I'm just going to run the cell here. We will use PyTorch, we will use NumPy, we will use Matplotlib, we will use Torch Vision, and some utilities and some sub-modules from each of these libraries. Now we can download the data. So this is the MNIST dataset, and we can create a PyTorch dataset using the MNIST class from torchvision.datasets. So we use the MNIST class, give it a root path where the data will be downloaded, and set download to true. And one thing we also want is that these images should be loaded up as PyTorch tensors. So by default, images are loaded as PIL images, which is a format used by the Python imaging library. Now the PyTorch provides a 2-tensor transform. This 2-tensor transform can be used to convert these image objects into PyTorch tensors so that we can train deep learning models using them. So here you can see that the dataset gets downloaded, and you can check how many elements there are in the dataset by using len. So you do len dataset, and that gives you the number of elements. So there are 60,000 elements here, or 60,000 images and 60,000 labels. Now we can take a look at a sample from the dataset by just invoking dataset 0. And you can see here that it contains this tensor, which is the image tensor, and right at the end you will also see that it contains a small label. So the image is represented as a tensor, and then you have this label which is represented using a number. Now it would be nice to see this image, display this image within the Jupyter notebook. And remember that these images are now PyTorch tensors, and they have the shape 1 by 28 pixels. So the first dimension represents the color channels. Since this is a grayscale image, there is only one color channel. But if you had a RGB image, you would have 3 color channels. Then the second dimension represents pixels along the height. Second, which is basically, if you look at an image like a matrix, then the rows is what this represents. Each element, each pixel along the height represents 1 row. And the third channel represents the pixels along the width. So each element in the third channel represents 1 column. Now we can use the plt.imshow method from Matplotlib to display these images, but there's a small change we need to do here, because plt.imshow expects the colors to be the final channel rather than the first channel. So it expects the color channels to be the final dimension rather than the first dimension. So all we need to do is use the permute method. So we take an image, we get the dataset, the first element from the dataset, and we get the image and the label out of it. Then we take that image, which is a tensor of 1 by 28, and we permute its dimensions. So we simply move the data around so that now the dimensions, the 0th dimension goes to the last position. So the color channels are now the last dimension, and then the height and width become the first dimension. So you can check this here. If we simply take this image label and we check image.shape, you can see that image.shape is 1 by 28. But if you permute the dimensions, you set 1, 2 and 0. And now you check the shape. Now it becomes 28 by 28 by 1. And now it can be passed into plt.imshow. So let's do that. Okay, let's just run this once again. Okay, seems like there seems to be a small error here. Let's try and fix this error. So here we're taking image and then we're taking the image and we are permuting the dimensions of the image. So let's see, let's permute the dimensions. So this is the image permuted, and let's check image permuted.shape. So there you go. Now the image, we have taken the dimension from the first dimension and moved it to the final dimension. And then let us now try and plot the image permuted tensor. Okay, there seems to be an error here. Now one simple way to resolve this is actually to skip the final dimension altogether. So we'll simply, since we only have one channel within the image, we are just going to pass image 0 here, and image 0 you can see will have the dimension, image 0 will simply have the dimension 28 by 28. And this is another thing that you can do. You can simply pass a 28 by 28 matrix into plt.imshow and that will plot it for you. Now, next step that we need to do is to use the random split helper function to create a validation set out of your data. As we learned in the last tutorial, we have a training set and we have a validation set. Now the training set contains images that will be used for training the model, and then the validation set will contain images that will be used for evaluating the model while we are training it. So to evaluate its performance on data which has not been used to already train the model. And we will use a validation set size of 10,000. So we will take a training, the training size then becomes the length of the data set minus the validation size. So that is about, let's see what that number is. So that's about 50,000 because there are 60,000 training images in total. And we do that using random split. So we pass the data set into the random split function, and that takes the training size and the validation size and it returns two data sets from the same data set. Now this one is the training data set with 50,000 images and this one is the validation data set with 10,000 images. So now we have loaded the data set, we have looked at certain images, and we have extracted out a validation set and separated out a training data set. The next step, if you recall, while training a model is to create data loaders, because we want to train the model using gradient descent. And while doing gradient descent, we want to work with data in batches. So we are going to set the batch size to 128. And then we can now create data loaders. So we have the train loader and the val loader. So we take the training data set and the batch size, and we set shuffle equals true, and that creates a data loader with the given batch size. Similarly, we are going to create a data loader for the validation data set. Now we have a couple of other arguments here. Num workers equals 4 and pin memory equals true. So now you can check out what this does. Maybe you can look through the documentation, but what I'll tell you is this incorporates some parallelism into the data loading process, so that if the machine where all this code is running, if that has multiple cores, then multiple cores can be used to load the data in parallel. Okay, so now we have created data loaders. Now it would be nice to visualize a batch of data in a grid and we can do this using the makeGrid function from Torch Vision. So once again, what we'll do here is we are going to get a batch of data from the training data loader. So we get a batch of data from the training data loader here, and maybe let's look at it step by step. And then we simply look at the shape of that batch. So here we have the shape of the batch, and let's just look at one batch here. So we'll break out. Yeah, so we get images and we get the images and we check the shape of the batch of images. It is 128 by 1 by 28. This is what we expect. Each image is 1 by 28 tensor. Next, what we do is we then invoke makeGrid. So if we now invoke makeGrid, so now we can check the shape of the grid after invoking makeGrid. So you have makeGrid images, and what makeGrid does is it takes a batch of images and converts it into a single image by putting all the images in a grid. So we need to specify how many images need to be put into a specific row, into each row. And you can see now, if we check the shape of the output, the grid has a shape 3 by 242. All right. So this is what it does. it creates a grid of data, and then we can take this grid of data, and here once again channels is moved to the front. So we need to move the channels to the end, and we can take that tensor, which is the height by width by channels, and pass it into plt.imshow. Okay, and that's what we are doing here. So we create a grid of data using the images, and then we permute the channels, move the channels dimension to the end, and then finally we break out here, and that gives us this batch of data. So here we have a batch of about 128 images. You can see images of all different types, and some of these can be quite confusing. For example, this could be a 7 or a 1. This could be a 4 or a 9, and that's what makes this dataset quite challenging. All right, so now we have dataset loaded in batches, and probably this is the point at which we would start defining our model. And before we formally define our model and train it, let's talk about what we are going to do here that is different from last time. So this time we will create a neural network with two layers. We will have a hidden layer and an output layer. Additionally, we'll use an activation function between the two layers. And this activation function will allow us to capture non-linear relationships between the inputs and the outputs. So let's look at a step-by-step example of how hidden layers and activation functions and non-linearity works and what this is all about. So now first let us create a batch of input tensors. So we can take a batch of input tensors, and we know that when we take a batch of input tensors, it has a shape 128 by 1 by 28. But we know that when we want to put an image into a nn.linear model, into an nn.linear object, we need to first flatten it out into vectors, right? Because ultimately what we do inside an nn.linear model is we take the input, treat it as a vector, and multiply that input with a weights matrix. We compute the dot product of the input with the weights matrix, and then we add a bias. So keeping that in mind, what we are going to do is we are going to reshape the images. So rather than having 1 by 28 images, we are going to have images, each of which is now flattened out into a vector of size 784. So here we have a batch of input tensors or input vectors. So we have 128 input vectors of size 784, and now we are ready to pass this into a model. So next, let us create an nn.linear object. So remember the nn.linear class, we used it in linear regression and also in logistic regression. It simply contains a weights and a bias matrix inside it, and you can specify how many inputs you're going to pass in. So in this case, we are going to pass in 784 inputs, and this nn.linear object will serve as our hidden layer. So we will have two layers in our model, a hidden layer and an output layer. So this will be our hidden layer, and because this is a hidden layer, we get to control the output. So we will set the size of the output from the hidden layer to 32. Now normally if we just had one layer, then the size of the output is determined by the number of outputs that we need, the number of target labels that we have. For example, for the MNIST dataset, you have images of size 1 by 28, which is 784, and you have 10 labels, so you need 10 outputs out of it. But since this is a hidden layer, we are going to set it to 32, and we'll see how to later convert this into 10 outputs that we need for our final loss computation and gradient descent and so on. So this number can be increased or decreased to change the learning capacity of the model. So feel free to experiment with this here. Instead of putting in 32, you can put in 64, you can put in 16, and you can see how it affects the results and the training time. So here we have the input size, which is simply inputs.shape -1, which is 784, and the hidden size is set to 32. Now we are ready to create our first layer in the model that we will finally create. So this is nn.linear. This takes the inputs of size 784 and converts it into outputs of size 32. Now we can compute intermediate outputs for each batch of images by passing inputs through layer 1. So for example, here we look at inputs. It has the shape 128 by 784, flattened images, and we take those flattened images, those vectors, a batch of vectors, which is essentially now a matrix. If you put a batch of vectors together, you get a matrix. You put that matrix into layer 1 and you get back outputs. And as you might expect, the outputs have this shape 128 by 32. So it's a batch of vectors, each of size 32. So the image vectors of size 784 are transformed into intermediate output vectors of size 32. And just to revise, just to be super clear about what is happening here, we can actually ensure that what's going on inside is simply a matrix multiplication. So here what we're doing is, instead of passing these inputs into layer 1, we will do a direct matrix computation. So here we take the inputs and then we do a matrix multiplication of the inputs with layer 1 dot weights transposed, and then we add layer 1 dot bias. Okay, so we take the inputs, we multiply it with layer 1 dot weights, and we add layer 1 dot bias, and you can check that it has the exact same shape, 128 by 32, as the layer 1 outputs. And in fact, if you check the values of layer 1 outputs and layer 1 outputs direct, because we are performing the same computation once using PyTorch built-ins and once using basic matrix operations, they will have the same values. So you can actually check that using torch.allClose. Now, because these are floating point numbers, normally you cannot use the equal to operator to compare the values of floating point numbers, because the order of calculations can sometimes change the actual values that you get by small magnitudes, because floating point numbers are not precise. So we can use torch.allClose to ensure that layer 1 outputs and layer 1 outputs are direct, are all the values within 0.001. That means, are they all very close to each other? And when we do that, we get true. Okay. Now, the reason for doing all this is simply for us to once again reinforce the point that when we use an nn.linear object, we are simply creating a linear relationship. So the layer 1 outputs and the inputs have a linear relationship. That is, each element of layer 1 outputs is a weighted sum of elements from the input. For instance, if these are the input pixels, 784 pixels, and this is one output out of layer 1 for a particular image, you can see that it is simply obtained by multiplying each pixel with a bunch of weights and then adding up that weighted sum to get this output. Okay. Now what happens is, we start, if you recall gradient descent, we start to train the model, and we start with random weights, but we slowly improve the weights to make the model closer to the relationship between the inputs and outputs, so that it makes better predictions. But because of the structure of layer 1, it can only capture linear relationships between the inputs and outputs, and that is a very big limitation. Now this is where the activation function comes into picture. Now what we do is, we will use the rectified linear unit function. Now we'll talk about this function as the activation function for the outputs of the hidden layer. Now before we do that, let's learn what ReLU is, and it's also called ReLU, the rectified linear unit. It has a very simple formula. ReLU of x is simply the maximum of 0 or x. That means if the input given to ReLU is negative, it simply sets it to 0. And if the input given to it is positive, it simply retains that same input. It returns the same input as the output. Okay, so it simply replaces negative values in a given tensor with the value 0. And this is how you can visualize it. It's a very simple function. All it's doing is removing negative values, replacing them with 0. And here is an example. So here we create a tensor using torch.tensor, and then we set f.ReLU. So we call f.ReLU on this tensor, and you can see here that the positive values are retained, but the negative values go away. Okay. And now what we can do is, we can apply the activation function to the outputs of layer 1. So these are the outputs that we just obtained. Let's look at layer 1 outputs.shape. So you can see here, layer 1 outputs, we obtained 32 outputs, or a vector of size 32 for each of the 128 images. So we call f.ReLU and we pass into it layer 1 outputs, and that simply gives us a vector or a tensor of the same size called ReLU outputs. In fact, we can print its shape. So remember that ReLU is a function that applies element wise. It does not combine the different elements of a tensor in any way. It applies the ReLU function to each individual element within the given tensor. So let's check ReLU outputs.shape. And let's also check what is the minimum value, what is the lowest value, torch.min of layer outputs, and what is the lowest value inside ReLU outputs. So if ReLU gets applied properly, what we should be able to see here is that one, ReLU outputs.shape is the same as layer 1 outputs.shape. So we've not changed anything here in terms of the dimensions of the tensor. But if you see the minimum value, you can see that the minimum value of layer 1 outputs was minus 0.75, but the minimum value in ReLU outputs is 0. Now there you see already that we have now created some sort of non-linearity, right? Because as it's applied to all of these values together, you can see that this ReLU function is no longer a straight line. It is It is two straight lines, but that is already a point of non-linearity. Okay. Now we know that the ReLU outputs and inputs do not have, the original inputs do not have a do not have a linear relationship. You cannot write this as a simple linear equation, as a simple matrix multiplication, because there is this non-linear function involved. And we refer to ReLU as the activation function because for each input, certain outputs are activated. Those are the outputs with non-zero values, while other outputs are turned off. So what we are doing here, if we go back to this picture, is once again we are converting the inputs into outputs by doing a linear transformation, but then whichever outputs are negative, we are replacing them with 0, and whichever ones are positive, we are retaining their value. So in some sense, the threshold, the 0 threshold decides which outputs get activated. Okay, so now we have our first layer, hidden layer, which gave us 32 outputs, but we have 10 target labels. So we need to ultimately get back 10 outputs for each image. So now what we are going to do is create an output layer to convert vectors of the length hidden size in ReLU outputs into vectors of length 10, which is the desired output of our model, since there are 10 target labels. So here we have the output size of 10, and we are going to create layer 2. The input to this was going to be hidden size. So each vector or a batch of vectors from the hidden layer passed through the ReLU activation, and the output is going to be output size. So let's create the layer, and let's pass the ReLU outputs into layer 2, and that is going to give us the outputs of layer 2. And let's check the shape of layer 2 outputs. So you can see that ReLU outputs had the shape 128 by 32, and before that the inputs had the shape 128 by 784. So we took inputs of shape 128 by 784, which were originally images of 128 by 1 by 28, converted them into these 32 sized vectors, and then we converted those into 10 sized vectors of size 10. And now we can use this output to compute the loss. So now we can actually do our loss computation, and we can perform gradient descent, and then we can adjust the weights. So this time when we compute the loss, then the loss is a function of both the weights of layer 1 and the weights of layer 2. And that's a very interesting thing. This time when we perform gradient descent, it's not just that layer 1 will get updated or layer 2 will get updated, but both of their weights will get updated in the process. Okay, so this is how you would probably pass layer 2 outputs into labels and then perform gradient descent, and we will do that. And now this is where the key insight comes into picture. So what we have done is that our model is transforming these inputs into layer 2 outputs by applying a linear transformation using layer 1, followed by a non-linear activation using f.ReLU, followed by another linear transformation using layer 2. So you can actually verify this. You can verify that if you simply write this in a single sentence. So here what we're doing is we're taking the inputs and we are multiplying them with layer 1.weight and adding layer 1.bias. Then we are applying f.ReLU to it, and then we are multiplying that result by layer 2.weight and adding layer 2.bias. So all that we have done so far through multiple steps, we are now writing the whole thing in a single step, right? Essentially, it is also the same as writing inputs passed into layer 1, passed into f.ReLU, passed into layer 2. Okay. And these outputs you can verify are the same as the layer 2 outputs that we have computed step by step above. All right. And now, since outputs and inputs do not have a linear relationship because of the non-linear activation function, now what happens is we have suddenly given our model more power. We have given the structure that we have set up within our model because of the non-linearity. It can now capture non-linear relationships between the images and their labels. So in other words, the non-linearity is making our model more powerful and versatile. Another thing to keep in mind is the hidden size. Remember, we had a hidden size of 32 here. Now this is something that is up to us to decide. Now in linear regression and logistic regression, the size of the nn.linear object was determined by the number of inputs and outputs. But here, since we have a hidden layer, we can decide how many outputs we are going to have, how many intermediate outputs we are going to have from the hidden layer. And that is really powerful because the more outputs you include within your hidden layer, the more parameters your model gets. So the more relationships it can start to learn. That is one way to increase the power of the model. Another thing you can do is you can also introduce new hidden layers and apply the same non-linear activation function after each hidden layer. And that is also going to let it learn complex multi-layered relationships. And that is really all there is. And that is why we're spending so much time here, because it seems pretty straightforward that we're simply adding some non-linear activation between a bunch of matrix multiplications. But this is exactly what a neural network is. There is nothing more to it really. A deep neural network is simply a neural network with one or more hidden layers. And the universal approximation theorem of neural networks states that a sufficiently large and deep neural network can compute any arbitrary function. That is, it can learn any kind of rich and complex non-linear relationships between inputs and targets. So for example, here are some examples of things that you can do with neural networks with using deep learning. So you can identify if images contain a particular digit, but you can identify if an image contains a cat or a dog or something else. You can identify the genre of a song using a 10-second sample. So all you need to do is represent the song as the audio as a matrix and then put that as an input to a neural network and get an output, perform gradient descent. You can classify movie reviews as positive or negative based on their content. Once again, you take the text, you somehow represent it as a matrix and you pass it through a neural network and perform gradient descent. You can navigate self-driving cars using a video feed of the road. So you take the video feed of a road from a camera and take that and run it through a neural network, train it using gradient descent, and it can figure out whether your car should move left or right or hit the brakes. You can translate sentences from English to French and to hundreds of other languages, and you can convert a speech recording to text and text recording to speech and vice versa. And there are many more applications, and this is such a simple but such a powerful model of learning. And it's hard to imagine how the simple process of just multiplying input matrices with randomly initialized weight matrices and then applying non-linear activations and then adjusting the weights repeatedly using gradient descent can yield such great, such astounding results. But that is really all it is. It's matrices all the way down. And why it is sometimes so hard to comprehend is because deep learning models often contain millions of parameters, because suddenly you have these hidden layers and you can make these hidden layers as large as you want, and you can have as many hidden layers as you want. So deep learning models often contain millions and sometimes billions of parameters, and together each of these parameters learns a specific thing about a specific relationship between the inputs and the outputs, and together they can capture far more complex relationships than the human brain can comprehend or describe. But in some sense we do the same. We are able to instantly identify a cat and a dog by looking at a picture, even though we may not be able to articulate exactly what the differences are. So in some sense, and this is why neural networks are called neural networks, because in some sense they are inspired from the way the brain learns, and the way the brain learns is exactly somewhat similar, where all of these things, as you look at a lot of data, you start to form these parameters, these neural connections, these neural patterns within your brain, which you can use later in new situations to identify and classify new objects. Okay. Now, one last thing I want to mention here before we move on is that if we had not introduced a non-linear activation between the two linear layers, the final relationship between the inputs and outputs would still be linear. And this is something that you can verify, but here is a simple refactoring. So here we have written out the expansion of layer 1 inputs passed into layer 1 that passed into layer 2. So you can write it like this, and we are calling the outputs 2. And then here, if you go through this piece of code, you will see that we are creating a new linear layer called combined layer, and we are manually setting the weights and the biases of this combined layer using a combination of the weights and biases of the two linear layers. And it's simply a matter of expanding these brackets. So if you simply open up these brackets and then rearrange the brackets in a different way, you will find that you can create a combined weights and you can get a combined bias term. And now here what you can see is inputs passed to layer 1 passed through layer 2 is the same as input passed through the combined layer, which is again a linear layer. Yeah, let's run this. So which is again a linear layer. Okay, so here you can see that outputs 2 and outputs 3 are almost equal, all close. So that tells us that this one activation function changes everything. It gives you the power to learn nonlinear relationships. And really this is something that has defined the progress in deep learning over the last decade or so. Okay, so now we have the basic idea of how to give our model more power, and the rest of the process will be pretty much identical to what we have seen so far in the previous 2 lessons, and we'll go through it step by step. But in the meantime, let's save our notebook first. So let us install the Jovian Python library, and let us import Jovian and run jovian.commit. What this is going to do is going to ask you for an API key, which you can get from your Jovian profile after logging in, and you can paste it here. And once you do that, it captures a snapshot of your notebook, and it takes the notebook and puts it onto your Jovian profile so that you can review it. So now you have a read-only version. Even if the Colab instance shuts down, you will not have a problem. You have a read-only version of the notebook, and you need to run it whenever you need to run it. You can come to run it on Colab or any other platform of your choice. So do keep saving your notebook for time to time so that you do not lose your work. And let's move ahead. So we're now ready to define our model. Now, as we just discussed, we'll create a neural network with one hidden layer. And this is what that means. Instead of using a single nn.linear object to transform inputs or pixel intensities into the outputs, which is class probabilities, we will use 2 nn.linear objects, and each of these is called a layer. And the first one will transform the input matrix into a matrix of batch size times hidden size. So each input of vector of size 784 will become a vector of size 32 or 64 or whatever it is. Then we will apply a non-linear activation, and then we will pass them through an output layer, which will give us the outputs of size 10 for each image. And these 10 outputs will be then interpreted as class probabilities, and we will use the loss function called cross entropy and perform gradient descent. All right. So this is what it looks like visually. We have these inputs. We are first passing them through the hidden layer, then applying an activation and getting the output out of it. Then we are comparing that with the target output using cross entropy. So let's define our model by extending the nn.Module class from PyTorch. Now we were doing exactly what we have done in the last lesson. So please go back and review the last lesson if you haven't watched it already, or you need to review a specific part of it. So in nn.Module, what we need to do is we need to define 2 functions, init and forward. Now init is the constructor. Now we will make our model a little more generic. So this time in the init, in the constructor, we will accept the input size, hidden size, and output size, so that you can actually use this model with different kinds of data. If your images are not 28 by 28, maybe they're 64 by 64, then you can pass in the input size of 64 times 64. If you have 100 classes instead of 10 classes, then while creating the object, while creating the model, you can pass in the output size of 100. And then you can also set the hidden size here. So we are going to set the hidden size to 32 when we create a model, but you can try different hidden sizes of 64 and so on. So now inside the constructor, we define 2 things. We define the hidden layer and the output layer. So we define self.linear1. That is nn.linear takes the input size, converts it to hidden size. Then we do self.linear2 takes the hidden size and converts it to output size. Now, if you want, you can introduce more hidden layers. So you can go linear 1, linear 2, linear 3, linear 4, and so on. And just the final layer is the output layer. Then we have this forward method. So in the forward method, we get a batch of images from the training data loader. We flatten those image tensors into vectors. And this is simply the code to flatten it from 1 by 28 images to vectors of size 784. Then we take those outputs, we take those flattened vectors, a batch of flattened vectors, pass them into the first linear layer. We get back the intermediate outputs. Then we apply the activation function using f.relu, so that it simply replaces the negative values in the output tensor in the intermediate output with 0. Then we get predictions using the output layer. So we simply put the intermediate output of the activation into the linear 2 layer, and we return it. And that's all there is. So we have the init method and the forward method, and these are the only 2 required methods. But we had also defined some other additional methods to ease our training process. So we have a training step method, and the purpose of the training step is to take a batch of training data and return the loss. So this returns the loss for a batch of training data. So this is going to take a batch of data, get the images from it, pass the images into the model, which is self, and that is going to internally invoke the forward method of the model, and that is going to give us the output. So nn.Module has this functionality where when we pass something into the model, when we use the model as a function, then automatically it performs some setup and then invokes the forward method. It invokes the forward method of the model, and then it returns the output, which is the output of the forward method. And then so in training step, we are getting the output from the model, and then we are calling f.cross entropy. So we're taking the output and the labels and putting them into the loss function to get the loss and returning the loss. So that's the training step. And similarly, we have the validation step. So I'll let you go through it. But the basic idea here is we generate predictions from a batch of validation data. Then we calculate the loss for that batch. And we also calculate the accuracy of that batch, which is in the batch of 128, how many predictions, what percentage of predictions did the model get compared to the labels. Then we have a couple more helper functions, one called validation epoch end. All it does is it takes the results from each batch of validation data. So we have, for every batch of validation data, we get a loss and an accuracy, and it simply takes the averages of those. So once again, you can read through the code here. We've gone through it in more detail in the previous lesson, but the idea here is it combines the losses and accuracies from multiple batches to return the overall validation loss and the overall validation accuracy. And finally, we have this method called epoch end. This method simply prints out at the end of each epoch, it is going to print out the epoch number, the validation loss, and the validation accuracy. Okay. And we will see where these functions get used when we actually perform the training. So we will define the fit function as we had done the last time. And now we also need to define an accuracy function which calculates the accuracy of the model's predictions. You can see that this accuracy function is used here. All it does is it takes the output of the model. So for each input, for each image, we get back 10 outputs. And then remember, we interpret those outputs as probabilities for each of the 10 labels. So then we say that the prediction of the model for a particular image is simply the output which has the highest probability. For example, if for a particular image, the outputs are 0.1, 0.3, 0.2, 0.1, and so on for the 10 classes, then we say that the output 0.3 has the highest probability. So this is the prediction of the image. Okay. So that's how we get predictions from our image. And here we are simply comparing the predictions of our image with the actual labels that are given to us in the training data, and using that to calculate the accuracy or the percentage or fraction of correct predictions. Okay, so now we are ready to create a model with a hidden layer with 32 activations. And now you can change this. You can change this to 64, 128 and experiment with it. Input size and number of classes cannot be changed. Now we are creating this model, and we can take a look at the model's parameters. So now if we go through model.parameters, so if we say for t in model.parameters, we are going to print t.shape. So for each parameter matrix, we're going to print the shape. And since we have two linear layers, we have linear 1 and linear 2, we can expect to see one weight and one bias matrix for each of the layers. So here are the weight and bias for linear 1, the hidden layer. Now it takes 784 inputs and converts them into 32 outputs. That's why they have this shape. And then linear 2 takes 32 inputs and converts them into 10 outputs. That's why it has this shape. Now let's try and generate some outputs using our model. So what we'll do is we will put our training loader in a for loop that will give us a batch of images and a batch of labels. And we're going to put the batch of images into the model and get back a batch of outputs. And then we are going to just check the shape of the outputs as well. So here we are checking the shape of the outputs, and we're going to check the shape of we're going to check the loss as well. So we can do both of those things here. So here we have a batch of data for which the loss is 2.28 and the outputs have the shape 128 by 10. So as expected, for each image, we get back 10 outputs, and these are some outputs. Now remember, these outputs can have negative values, positive values. So what we do is we apply the softmax function to convert these into probabilities. And once again, you can refer to the previous lecture, the previous lesson to learn more about it. And then we pick the value with the highest magnitude as the prediction. So in this case, for example, it seems like the highest magnitude would be for this element. So the prediction of the model would be this one. 0. The model is predicting that the first image represents a 0. Okay. So now we have set up our model and we need to train our model. And now because we have so many parameters inside our model, we have 32 times 784 plus 32 times 10 plus 32 plus 10. That's a whole bunch of parameters. And we have to train for over 60,000 images. So we use 50,000 images for training and we use 10,000 images for validation. So that is a lot of matrix multiplications and that training can take a long time. Now this is where a GPU comes into picture. As the sizes of our models and datasets increase, we need to use GPUs to train our models within a reasonable amount of time. And GPUs or graphics processing units or graphics cards contain hundreds of cores optimized for performing expensive matrix operations like matrix multiplications, additions, inversions on floating point numbers very quickly, making them ideal for training deep neural networks. So they were invented for games, but they are applicable here as well, because a lot of the math that is involved in rendering games is the same as the math that is involved here, which is matrix operations really. And you can use GPUs for free on Google Colab and on Kaggle, or you can rent GPU powered machines on services like Google Cloud Platform, AWS and Paperspace. Now we can check if your GPU is available and connected to the machine where this code is running. And remember, although we are writing code in our browser, the code is actually executing somewhere on Google servers, and we have just enabled the GPU runtime. So that server where this is running is connected to a physical hardware GPU. And not only do you need to have the GPU connected, you also need to have the NVIDIA CUDA drivers installed. So CUDA, NVIDIA is a company that manufactures these GPUs, and CUDA is the language that is used to communicate with the GPU. So you need to have some drivers installed for the GPU. So we can check if all of this is in order by checking torch.cuda.is available. So when we invoke torch.cuda.is available, if you get the value true, that means you have access to a GPU that you can leverage. If you get the value false, that means you do not have access to the GPU. So maybe your computer, your machine does not have a GPU. For instance, on Binder, you will get the value false, or on your own computer, you might get the value false if you do not have a GPU. And that is where you will then have to check if you want to get a computer with a GPU, and if you have a GPU already, do you have the right drivers installed? But as such, you can use cloud resources. There are ample free cloud resources for you to do all the deep learning projects, all the advanced neural networks that you want to train. So you do not need to go out there and buy a GPU if you don't have one. Okay, now let's define a helper function to ensure that our code uses the GPU if it is available and defaults to using the CPU if it isn't. And this is something that you should always do. Never write your code assuming that there is a GPU present, because there will be circumstances where you might have to just run it without a GPU. So that's where we are going to define this function called getDefaultDevice. This is going to return a device. A device object is simply a pointer to a particular execution target, either a GPU or a CPU. So we check if torch.cuda.is available, then return torch.deviceCUDA. So torch.deviceCUDA returns a pointer to a GPU, and torch.deviceCPU returns a pointer to the CPU. So then we call getDefaultDevice and we store it in the variable device. And now we can see that device has the type CUDA. That means our default device is GPU. And now we can use this device to move our data to the GPU. Okay. And this is how we'll do it. So we are defining this function toDevice, which takes some data, and it takes a device, and it simply moves the data to that device. So now the data can either be a tensor or a model. Now if the data is a tensor or a model, then this if condition does not hold. So it simply comes to this part. So both tensors and models in PyTorch have a to method, and the to method takes a device. So you can simply invoke the to method with the target device, and the tensor will take all of its data, which by default would be sitting on the CPU, and then it would transfer it over onto the GPU. So just as your CPU is connected to some RAM or memory within your computer, same way the GPU also has its own memory. So your CPU memory might be quite large, like 16 GB, 32 GB or 64 GB. And GPU memory is typically smaller. So GPU memory is more in the range of 4 GB, 8 GB, 12 GB, 16 GB. But GPU memory is connected directly to GPU cores. So that's why data needs to be moved into GPU memory so that GPU cores can operate on it. And data.to, calling that on a tensor or a model, is going to move it to that given device. Okay. Now we've written some extra code here. This is not really necessary, but all this is saying that toDevice function can also accept a list of tensors or a tuple of tensors, so that if we want to move multiple tensors at once, we can do that using toDevice. Okay. And you can, but as such, you will be able to run this code even without that. The key idea here is tensors and models have this to method available where which you can use to move them to a particular device. Now let's see how to move. Let's look at an example of how to move data to the device. Now let's take a batch of images. Let's take a batch of images and a batch of labels from the training data loader. And then let us take the images. Let's check the shape of the images. Let us move the images to let us check the device of the images. Then let us move them to the device which we had created using get default device, which is the GPU. So we call toDevice images with the GPU, and then we print images.device. So you can see here that the images have the shape 128 by 1 by 28, a bunch of image tensors, a batch of image tensors. Initially they are on the CPU, but when we invoke toDevice, they are then moved to the GPU. And that's all there is. Now that batch is moved to the GPU. Now this is something that we will have to manually do. Each time we get a batch of data, we will have to move it onto the device or onto the GPU. And then once the processing is done and we try to move the next batch, then the previous batch of data is automatically vacated by the GPU. So to access this, to avoid writing too much additional code, we will define a class called device data loader. What this class will do is this will wrap our existing data loaders. So we'll take a training loader and we will pass it into device data loader, and we'll take our validation loader and pass it into device data loader. And what this device data loader will do is that it will automatically move batches of data to the selected device. So let's look at its usage first, then we will see how it is defined. So we have this device data loader, and this device data loader is going to trap the training loader and take the device. And similarly, this device data loader, here we are passing the validation data loader and the device. So both of these will get wrapped. And then what will happen is when we try to access a batch of data within a for loop from a validation data loader or device data loader, they will automatically be moved. The batch of data will automatically be moved to the selected device that we have passed here. Now, how do we do that? To do that, we need to define a PyTorch data loader. And a PyTorch data loader, fortunately, does not require extending any class. A PyTorch data loader simply needs to define two methods, iter and len. Now iter defines how the data loader will behave when it is used within a for loop. And the way we are going to do that is, first in the constructor, we're taking a data loader and we are taking a device. And then we are setting in the device data loader object, we are setting self.dl as the data loader and self.device as the device. So in the constructor, we are simply taking the arguments and then storing them in local variables within the object. Remember that in PyTorch classes, in the methods, the first argument represents the object that will get created when you instantiate or use this class. Okay, so we are simply taking the data loader and the device and storing it within the object as self.dl and self.device. Then the iter should return a batch of data. In fact, it needs to yield a batch of data, and we'll talk about that. So what we do is we simply run a loop over self.data loader, and then we simply yield the same batch of data that we get, but we are going to move this batch of data to the specific device. And we are going to move to the specific device, which is self.device. So we get batches from the data loader and we move that batch into the self.device. So that is our iter method. And then we have this len method. All this does is returns the number of batches of data within this data loader. For this, we can simply invoke len on the underlying data loader because the number of batches has not changed. All that has changed is when the batch is being created and returned to the for loop. At that point, we want to move it to the device. Okay, so just go through this code step by step if it doesn't make sense, and see what happens if you do not have this, or if you do not have toDevice here, what difference does it make, and so on. Now the yield keyword in Python is used to create what is called a generator function, and a generator function can be used within a for loop. For example, if you have this function sum numbers, and now instead of returning something from sum numbers, if you say yield 10, yield 20 and yield 30, then what you can do is you can invoke some numbers and you can take that result and put it into a for loop. And you put that result into a for loop and you're going to get back, each loop is going to get back the value of a yielded by the last statement. So for example, the first element of the loop is going to be the result of yield 10. The second value in the loop is going to be the result of yield 20. The third value in the loop is going to be the result of yield 30. So in some sense, it maintains a counter and it keeps running through the yield statements. Okay, so now you can see that some numbers was used within value and we printed the values 10, 20 and 30 within the for loop. Now in the same way, what we did here is we said that we are going to run a for loop through self.dl and then we are going to yield the same batch of data but moved onto a particular device, so that when the data loader itself is used within a for loop, it will in turn internally keep using values from the original for loop and moving those batches of data to the device. Okay, so now we can wrap our data loaders using device data loader. So we say train loader and we take the device and the train loader and create a new training loader which is wrapped with device data loader. Similarly, we create a new validation loader, and you can see that we can now use the validation data loader or the training data loader in a for loop. And now this for loop, because we have defined the iter function where we have internally taken a batch and moved it to the device. So this for loop will automatically contain the resulting batches, where you can see that the batch of inputs XB or the batch of images is on the device CUDA, and the batch of outputs YB is also on the device CUDA here. All right. So all of this business is simply to set up, one, to figure out if we have a GPU available or not. Second, to create a default device object, which will either point to the GPU or CPU depending on which is available. And then to create this device data loader so that when batches of data are being loaded, they are automatically moved onto the required target device. Okay. And now, since we have done all of this process, now we have made it very seamless, or in some sense, we have abstracted away the logic of moving things to GPU simply by wrapping things into device data loaders and using the toDevice function. So our training is exactly the same. So nothing really changes in terms of our training. So we will define two functions, fit and evaluate, and we will use them to train the model using gradient descent and evaluate its performance on the validation set. Okay. Now we will not go into this in a lot of depth, and you can once again check out the previous tutorial. We spent a lot of time talking about these, but let's just quickly go through it. So here we have the fit function. It takes a number of epochs. It takes a learning rate. It takes a model. It takes a training data loader, the validation data loader, and it also takes the optimizer function. So by default, it uses the torch.optim.sgd, the stochastic gradient descent optimizer, but it can also work with other types of optimizers. Now, the first thing we do is we create an optimizer. So we take the optimizer function, which is the constructor optim.sgd, and we pass into it model.parameters. Now remember, model.parameters contains all the matrices that need to be updated during gradient descent. So if our model has 2 layers or 3 layers, so all the weights and bias matrices of all the 3 layers will get passed into the optimizer, so that when we are performing the update step of gradient descent, the optimizer is able to update all of them at once. And we pass in the learning rate, which is set here. The learning rate decides how much of a change we make to the weights in each gradient descent update step. Okay. Now for epoch in the range of epochs, so we run over the given number of epochs, and then in each epoch we have a training phase and we have a validation phase. So now we're going to see how the additional methods that we defined within our model are going to be useful. So we get a batch of data from the training data loader, and then we call model.training step. So each model that you train will use a different kind of loss function. And what we have defined in model.training step is the specific loss function that we are going to use for this model, which is f.crossentropy. So we are keeping our fit function generic enough so that we can use it with any kind of problem or any kind of model. And we are simply defining how the loss is calculated within our model itself. So we take the batch of data and put it in model.training step, and that gives us the loss. And then we take and then we call loss.backward. So this is a standard step. What this is going to do is this is going to compute the gradients of the loss with respect to the weights and biases of each layer, right? Because now the loss is not simply a function of a weights of a single layer. It is a function of a weights of a bunch of layers, one or more layers. Then we perform gradient descent using optimizer.step. So when we call optimizer.step, all the weights get updated at once because we have passed all the model's parameters into the optimizer, and they get updated using the learning rate, using the strategy defined within the optimization function. And finally, we reset all the gradients back to 0. So this is the training phase, and then we do it for each batch of the training data loader. And we do it in batches because it's faster to do it in batches. If you try to do it for the entire dataset at once, it may not fit within the memory, or it may slow down the training. So that's a training phase. Then we have the validation phase. So for the validation phase, we call the evaluate function. Now what the evaluate function does is it simply gets batches from the validation data loader. And then for each batch of data, it calls validation step. And if you recall, what we do in the validation step is we simply get the accuracy and the loss for each batch of validation data. And we collect all of those into outputs. And then finally, we call validation epoch end, which is going to combine the batches, the losses and accuracies of all the validation sets, all the validation batches, into a overall loss and accuracy by taking an average. So that's what evaluate does. It simply gives us the performance, the overall accuracy of the model on the validation data set, and the overall loss of the model on the validation data set. So we get that result, and then we take that result and we call model.epoch, and model.epoch end simply prints out a bunch of things. It is going to print out the epoch number. It is going to print out the validation set result, the loss and the accuracy, and that's it. And apart from that, we also take the result and we append it into a history. So we track the history of our training, and this is a very important part of training. You should always track how the model's accuracy and loss are changing over time as you train for multiple epochs. And that can give you hints about whether you need to train for longer time. That can give you hints about whether you need to decrease or increase the learning rate. Maybe if your model is training too slowly, you need to increase the learning rate. Maybe your model has stopped training and the losses are bouncing around. You need to decrease the learning rate. Okay, so that's our fit function. This is the standard fit function that we have used the last time, and we will continue to use it in the future lectures as well. We may add one or two small things, but this is essentially the gradient descent algorithm we have been using all along. Now, before we train the model, we need to ensure that the data and the model's parameters, which is the weights and biases of the model, are on the GPU, are on the same device, whether it's the CPU or the GPU. Now remember, we've already wrapped our training and validation data loaders using device data loader, so we do not need to move them. It's just the model that needs to be moved. So we can simply invoke the toDevice method on the model and pass it the same default device that we have. And that's going to put our model on the GPU. So now we have a model moved to the GPU, and let's see how the model performs on the validation set with the initial sets of weights and biases. Now remember, all of this we have done so far in the last 1 hour. We have not yet trained our model. We have simply set it up with 2 layers, one hidden layer with then an activation and then an output layer. And we have now defined a function that we will use to train the model. But before we do that, let's just check how it performs on the validation data loader. And now straight up, you can see here that that was pretty fast. If you had done the same thing on a CPU, this would have taken you a longer time. But here, 60,000 images were passed through a multi-layer neural network, and all the batches, all the losses and accuracies were calculated, and they were averaged out to return this in less than a second. And that is really the power of a GPU, which is it improves the computation by an order of magnitude compared to the CPU. And the initial accuracy is 17%, which is surprisingly a little high. Normally this is around 10%. And you might expect this from a randomly initialized model, since it is essentially making random guesses. And if you make random guesses out of 10 categories, maybe 1 in 10 times you might get it right. And that's why you get about 10, maybe a slightly higher accuracy. So now, finally, let us train the model for 5 epochs using gradient descent, and let us look at the results. And one thing you will notice is as you add more layers, as you add more parameters within your model and more layers and more hidden units within a hidden layer, you can actually use relatively higher learning rates. So this is something that you can experiment with. And one good strategy to pick a good learning rate is to maybe start around 10 to the minus 3 or 10 to the minus 4. And if your model is training very slowly, then keep multiplying the learning rate by 10. So if 10 to the minus 4 trains your model slowly, then try 10 to the minus 3. If 10 to the minus 3 is training your model still training slowly, or you think that it can still go faster, try 10 to the minus 2. At some point, your model will stop training and your loss will start increasing. And that is a point where you should probably stop at that point. On the other hand, if you see that your model's loss is bouncing around, it's not changing much, at that point you can reduce the learning rate. Okay, so this is a simple intuition, and you can always go in orders of magnitude of 10 or maybe of magnitude multiply by 5 if you need to. And towards the end, in 2 lectures down the line, we will also see how to automate this process. So we are going to look at a process of increasing and decreasing learning rates automatically. We're going to look at the strategy for finding good learning rates. But let's train the model now. So we're going to train it for 5 epochs with a learning rate of 0.5. And now you can already see that our validation accuracy just after the first epoch has shot up to 93.5, almost 95%. And that's pretty good because we trained our logistic regression model, which, remember, assumes a linear relationship between the pixel intensities and the output labels. And it could only get to about 87% accuracy after a lot of training, after even training for 20 minutes, 30 minutes or so. But here already just within less than a minute, actually each epoch took maybe less than 10 seconds. Just within less than a minute, we were able to get to almost 96% accuracy. And this was because, one, we got such a high accuracy because we now have non-linearity built into our model, and we have more parameters than before, and we can have even more parameters. You can try 64 and 128. The hidden size can be increased. You can add more hidden layers. And second, because we are training it on a GPU. So the model is more powerful and it is being trained more efficiently. And this is really what makes deep learning so powerful and so widely applicable, because we have the infrastructure to train huge models with lots of parameters really quickly. Now let's train our model for a few more epochs. It seems like the loss here seems to be bouncing around because the validation accuracy went up, then it went down. So we're going to now use a smaller learning rate of 0.1 and try and see if that can improve the accuracy further. So you can see now, as soon as we decrease the learning rate, we are starting to see a better accuracy, right? So this is the really hyperparameter choosing is one of the key parts of training machine learning models, and building this intuition is really important. If your model is training too slowly, increase the learning rate. If your model's loss is bouncing around, it's not improving, then try decreasing the learning rate. So we can now plot the losses and accuracies, and we can study how the model improves over time. So these are how the losses decrease. That starts out pretty high, falls pretty quickly, and then flattens out. And this is how the accuracies increase. Once again, you can see that it immediately jumps to almost 90% accuracy and then flattens out for the most part. So our current model outperforms logistic regression, which could only achieve about 86% by a fairly considerable margin, and it quickly reaches an accuracy of 97%, but it doesn't improve much beyond that point. And now I will let you figure out what you need to do to improve the accuracy further. So feel free to play around with this notebook, go up, change the model definition, try changing the number of epochs, try changing the learning rate, try using a different optimization function. So just see what are the different optimizers available in PyTorch. The more you experiment, the more you will learn. Now, as a final step, let us save and commit our work back. So take the notebook which is running here on Google Colab and put it onto your Jovian profile. So we just run jovian.commit once again, and this is going to put it onto our Jovian profile. Okay. Now we've trained our model and we have been tracking the overall accuracy and the overall loss, but it's also a good idea to look at some of the model's results on some sample images from the test set. So let's get some images from our test set. We have this MNIST dataset. Here we are just setting train equals false, and that is going to fetch the test dataset for us. And those images are going to get converted into tensors using the toTensor method. Now let us define a helper function predict image. What this will do is this will take an image, and then it is going to call on the image, it is going to call image.unsqueeze0. I'll let you figure this out what that does, but the result is that the image tensor gets converted into a batch of image tensors, except that the batch just contains one image tensor. Okay, so we create a batch using the image tensor using unsqueeze by adding a new dimension. Then we take that batch of image tensors and we move it to the device using toDevice. So that gives us the input. And then we put the input in through the model. So remember that the model and the input should be on the same device. This is a common error. If your data and your model are not on the same device, then you will get an error because your data is probably, let's say, sitting on the CPU, but your model is on the GPU. Both are different locations and both of these memories are disconnected. So when you want to perform an operation, either it has to be done on the CPU or on the GPU. Now the GPU does not have access to your computer's RAM, which is connected to the CPU, and the CPU does not have access to your GPU's RAM, which is connected only to the GPU cores. And this is a very common issue which sometimes trips people up. So keep that in mind. Whenever you get an issue, just make sure that your data is on the same device. And the way you can check device is simply by printing xb.device at any point. So just check the .device property of a tensor and that will tell you which device it is on. If you have multiple GPUs, sometimes you will find that your data has been moved to different GPUs. So do check not just whether it's a GPU or CPU, but also which particular GPU it is. And a lot of the cloud platforms are often connected to more than one GPU. So do keep that in mind. Okay, so now let's try this out with a few images. We get the first image from the test dataset. We get the image, we get the label. We show the image here and we then show the label as well. And then we show the prediction. So here, this is the image 7. It has the label 7 and we have predicted 7. Let's try another one. This is 2. And if you recall, our logistic regression model predicted that this was 8. And the reason for that was because a lot of the pixels that lit up here are the same pixels that light up while creating an 8 as well. So this is almost 70% close to an 8 in terms of the pixels that have lit up. And this is where a linear relationship breaks down, because now we not only need to look at which pixels have lit up, but also whether certain connections have been made or not. And that is more of a non-linear, a more subtler relationship, which can be captured by our neural network. And that's why you can see that the label was 2 and the prediction was also 2. Let's look at another example. Here we have this one more image. So this image, if you recall, the logistic regression model predicted this as a 4, because once again, this looks quite close to a 4. But the difference between a 4 and a 9 is that the 4 probably has a little bit of a pointed edge here, which the 9 does not. This cannot be captured by a linear model like logistic regression, because it's again only looking at pixel intensities and giving weights to those. But it can be captured by our feedforward neural network because it can learn non-linear relationships as well. Okay, and keep doing this because we are still only at 96% accuracy. So there are definitely 4% of images. So 4% of 50,000 is still a huge number. That's about 2,000 images or so. So you should be able to find some images where the model is not performing well, and identifying where a model performs poorly can help us improve the model by collecting more training data, or by increasing or decreasing the complexity of the model, or by changing the hyperparameters. And it's really, this is a very important step of deep learning that is often overlooked. You need to look at the results. You can't just keep blindly trying new strategies like just increasing the learning rate, decreasing the learning rate, training for more epochs, using bigger models, if you do not know what is wrong with your model. Sometimes what the problem could be with your data itself. You may have bad data, or you may have incorrectly labeled data, or you may just need to get more data for specific classes to give your model a better signal. Sometimes it may be difficult even for a human being to identify what's there in the data, and in which case it's harder for a model as well. So do look at examples. Always make sure that you're looking at individual examples. And then finally, after everything is done, at the very end, you should also calculate the final accuracy of the model, or the final loss of the model on the test dataset. So here we are taking the test, we are creating a data loader using the test dataset and a batch size of 256. And then we are wrapping it using a device data loader so that the data can be moved to the chosen device. And then we are calling evaluate with the model and the test loader and getting back a result. Once again, you get back the result with 97% accuracy. And we expect this to be similar to the loss or accuracy on the validation set. And if not, then we might need a better validation set that has a similar data and distribution as the test set. and the test set normally comes from the real world data. Okay, so now we're done with this model training. Now we've spent some time training this model, so we should save this model, and the way to save this model is to call torch.save, and we can save the model state dictionary. Now the state dictionary contains all the weights of the model. We don't save the model itself, we simply save its weights so that we can instantiate a new version of the model and load the weights when we need it. So we'll save the weights to a file MNIST feedforward.pth. And now we can, one other thing that we are going to do is we are going to log the accuracy and the result. So here what we're going to do is we're going to call jovian.log metrics, and here we're going to set test loss, which is the validation loss from the final result that we obtained, and test accuracy, which is the validation accuracy key from the final result that we obtained. Note that even though these say validation loss and validation accuracy, actually these are test loss and test accuracy, because we have passed the test data loader here. So we've logged those metrics, and finally we are now ready to commit the project. So we are going to commit this notebook, upload it to your Jovian profile. We are also going to include along with it these outputs. So the output MNIST feedforward.pth file, the trained weights of the model, we are going to attach that along with the notebook. So let's see what that looks like. So here we have this training deep neural networks on a GPU with PyTorch. This is the same notebook, and you can check here in the files tab along with your notebook. You also have these artifacts. You have this MNIST feedforward.pth. This is the output that we had uploaded. And then you also have these records. So these are the metrics, the test loss and the test accuracy that we just recorded. And what you can do as you record multiple versions, as you train different models, you can click on the compare button, and here you can actually keep track of what are the different ideas that you have tried and what are the results that they gave you. You can add some notes, or you can change the version title to reflect the different ideas that you've tried. Now this is also a very important part of machine learning, because in every machine learning project that you do, you will be trying out tens, maybe hundreds of different ideas. And unless you go about tracking those results in a structured fashion, you will probably end up repeating your mistakes, and you will not be able to capture learnings and move forward in a significant way. So that's why always note down your results somewhere. You can do that on a piece of paper, you can do that in a spreadsheet, or you can do that on Jovian itself by using jovian.log metrics, and then study the history, study all the ideas that you've tried, and use the insight from those ideas. Try to combine the good ideas, maybe try to combine a good network structure with a good learning strategy, with a good transformation of the data set, and so on. Right? As you combine many good ideas, your model becomes exponentially better. And it's often this discipline, and it's often this strategy that yields far better results than any level of optimization that you can perform on the hyperparameters themselves, or really more how long you train for or how much data you use. It's really these small things like looking at the bad examples, trying out different strategies, being disciplined about it, being structured with your reporting, that helps you find a better strategy for training your models better. Next, we have a few exercises that you can try out. So we have the assignment we'll go over, but there is also this starter notebook for deep learning models that I want to share with you. So here we have the starter notebook. This is simply replicating what we have done today, but this is doing it for a different dataset called the fashion MNIST dataset. So you can use a fashion MNIST dataset, and what you do here is this is the dataset source. So you can get the dataset. You can download the dataset from this source, fashion MNIST, and here we are training a machine learning model. For first, we are preparing the data. So we are, by the way, fashion MNIST is also included within PyTorch. So you can simply use the fashion MNIST class, and we are downloading the dataset. We are getting the test dataset. Then we check it has a similar size as the MNIST dataset. So it has 50,000, it has 60,000 training images. So we convert that into a validation set. So we have a validation set of size 10,000, and then we have a training set of size 50,000. Then we create training data loaders, validation data loaders, and test data loaders. And here we look at a batch of data. So this is what it contains. Instead of handwritten digits, this contains images of t-shirts, shoes, bags, and 10 different categories of things. Then we create a model. So we create a model here. So we have, once again, we create an MNIST model. Here we have hidden layer 1, hidden layer 2, and an output layer. So this time we are creating we are using 3 layers. Then we define the forward function where we pass the data, the input data through the first layer, apply an activation, pass it through a second layer, apply an activation, pass it through a third layer, apply an activation. And then the rest of this is really the same. We check if a GPU is available, we create a default device, we move the data to the device, and then we create we use the device data loader class to wrap our training, validation, and test loaders. Then we train the model. So we have the evaluate and the fit functions exactly as we have seen before. And we train the model using the MNIST model class. We move the model to the device and then we evaluate the model. We see it's about 10% accurate because once again, there are 10 classes. So on randomly, you will get 10% accuracy. Then we train the model using the fit function. So we call the fit function on the number of epochs and the learning rate. And we train the model and we see that we get to about 85% or so accuracy. So it looks like we have reached around 85% accuracy. So now the challenge for you is to take the fashion MNIST dataset, which is slightly harder than the MNIST dataset, and get it to above 90% accuracy. And then you go ahead and you can now start making some predictions on these samples. So here we have, this is an ankle boot and the prediction is ankle boot and so on. And then finally you can save the model. You can then commit the project and include the saved weights. And that's your deep learning model. And you can now take this starter notebook and you can apply to a whole bunch of different data sets. Now, if you're looking for data sets, a good place to find data sets is Kaggle. So you can go to kaggle.com/datasets. On Kaggle, you can find interesting data sets. So here you have this, for example, the way I would look for it is if you want to work with an image data set, you search for image classification. So here you have a whole bunch of image classification. So for example, here we have images of dogs and cats. Now you have these images of dogs and cats. If you log into Kaggle, you can download this. You can download these images using command. So let me just sign in here and I'll show you. So you can see here that you can actually download this data set quite easily. The one way to do it is to copy this API command. So you can just click copy API command. And if I run this notebook, so if I take this notebook and run it on Colab, yeah, you can take this notebook and run it on Colab. And the way to, what you need to do is you can simply paste the API command that you have here and you can run it. Now you will need to specify an API key and I will point you to the instructions here on how to use the API command. Let's just find those instructions here as well. So here you have the Kaggle public API, and to use the Kaggle public API, you need to set certain credentials. And now here are the instructions given to you on how to set the credentials. So you can follow the instructions here. Just search for Kaggle API and that will tell you the instructions for downloading the dataset into your Google Colab notebook using the Kaggle API. So these are the instructions that you need to follow. Okay, so you find your dataset from Kaggle and then you find your API credentials from the Kaggle API repository or the Kaggle API documentation. And then you can run this command, and by running this command, you can download this data into your Google Colab notebook, and then you can work with your Google Colab data. Okay, so do try it out. Now, one other thing is the assignment. So we'll discuss that. That is linked to here, the starter notebook. But before we do that, let's do a quick summary of what we've done. We created neural networks with one hidden layer to improve upon the logistic regression model from the previous tutorial. And then we use the ReLU activation function to introduce non-linearity into the model, allowing it to learn more complex relationships between the inputs and outputs. We defined some utilities to leverage a GPU if it is available by moving the input data and model parameters to the GPU and to the appropriate device. And we were able to use the exact same training loop, the fit function and the evaluate function that we had defined earlier to train our model and evaluate it using the validation dataset. Now there is a lot of scope to experiment here. So I encourage you to use the interactive nature of Jupyter so that you can play around with the parameters and you can try changing the size of the hidden layers. You can try adding more hidden layers. You can try changing the batch size and learning rate and see if you can achieve the same accuracy in fewer epochs. Can you get it done in 10 seconds, in 15 seconds? Is it possible? Can you get a higher accuracy of 99%? Compare the training times on a CPU versus a GPU. See, do you see a significant difference? So instead of using a default device, use torch.device CPU and see how that changes. Try running it on your own computer. try to see if you can get the same result with a smaller fraction of the dataset. So don't use the entire dataset, maybe split the training dataset into a sample, remaining and a validation set, and just use the sample for training. See if that helps, and try building a model for a different dataset. So here we have linked to a couple more datasets that you can try out. And the more you experiment, the more you learn. That's really all there is to it. So do spend some time, and also spend some time just thinking about it. And here are some more references for you to think about how neural networks can compute any function, can compute all of these rich relationships. So here's one, which is an interactive tutorial, an interactive visual proof that neural networks can compute any function, which is also known as a universal approximation theorem. You might have to spend about half an hour to 45 minutes on this, but if you work through this tutorial, you will understand specifically how neural networks can estimate specific functions. Then we have this video by 3 Blue 1 Brown. This is a visual and intuitive introduction to what neural networks are and what their intermediate layers represent. So here you can see that this shows you what we've discussed today using code and using some intuition. This shows you the same thing visually, and things become a lot more clear. If you're a visual learner, you will find this really helpful. So do check this out as well. You can also check out if you're more interested in the mathematics that is happening, because what we have done is we've understood what mathematics are involved, but you have not actually derived any formulae. So if you want to understand that part about how this entire formulation works, if you want to look at the mathematical notation, if you want to rigorously prove all the results, then you can go through these lecture notes from the Stanford CS 229 course for a more mathematical treatment of gradients and gradient descent. Okay, so that is all for this particular lesson, and we can then next we will talk about image classification using convolutional neural networks, which is a variation on feedforward neural networks. It's a special structure that we use. But before that, let's talk about the assignment. Now let's come to assignment 3, feedforward neural networks. And by the way, you have assignment 1 and assignment 2, and you can find the links here. And for each of these assignments, if you feel stuck at any point, there is a discussion forum link included in the assignment notebook, included on the assignment post. So please post your question and get help. It is not going to take a lot of time to work on these assignments, maybe a couple of hours, maybe 2 or 3 or 4 hours, not more than that. So please do spend the time. And if you try and set deadlines for yourself and try and complete one assignment every week, I guarantee you that by the end of this course, you will end up building a pretty significant project in deep learning that you can proudly showcase on your profile. So please try and work through the assignments. Now the third assignment is feedforward neural networks. And here what we're trying to do is we are trying to train many different neural network architectures to address a problem and get hands-on practice with what you will do in a real project, which is not so much about like understanding the theory or the mathematics behind things, because while that is useful, that is only useful up to a point. After a point, what you really need to do is you need to experiment with network architectures, experiment with hyperparameters, and try and get the best possible performance and results out of your model. So let's open up the starter notebook here. So you can go to the starter notebook, and now what to do, you can click the run button and click run on Colab. Now you can authorize and run your notebook on Colab. Now in this notebook, you are going to once again make sure that you have the GPU turned on. So go to runtime, click on change runtime type and change the accelerator to GPU. The other thing you should do is make sure to run the first cell so that the integration works properly. So now we're going to classify images of everyday objects using a neural network. Now the ability to try different neural network architectures is what makes deep learning really powerful. Remember, you can add hidden layers and you can increase the size of each hidden layer, and you can have many hidden layers, which is not really possible in shallow learning techniques like linear regression and logistic regression. So in this assignment, you will explore the CIFAR10 dataset. So the CIFAR10 dataset contains everyday objects from 10 classes. So it contains 60,000 32 by 32 pixel color images in 10 classes with 6,000 images per class. There are 50,000 training images and 10,000 test images. This is what the images look like. You can see here that these are the classes: airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And if we zoom in, you can see that it's sometimes pretty difficult to identify what's in these images because these are really low resolution images. This is supposed to be a deer, but it's not quite clear what this is. Similarly, this is supposed to be a cat, but you can't really tell if this is a cat or a tree. These are birds, and you have many different species of birds. You have many different types of cars or automobiles. And then you have another category called trucks, which is different from automobiles. So this can be a fairly confusing data set. Then you have ships, and then you have horses, and you have frogs in different situations. So it's not a very nice and clean data set like MNIST, where you have a black background and it's a grayscale image where you have a single digit. Here you can see these objects in real life scenarios, and sometimes, like for instance, somebody sitting on this horse. So you can see them in a real life scenarios. You will see a lot of variation in terms of their own color because these are different breeds of horses, and you will see a lot of variation in terms of the background. So this is a significantly harder data set, but the principles are the same. And in this notebook, you will work through the CIFAR10 dataset step by step. So we will set up a training pipeline to train the neural network on a GPU, and you will experiment with different network architectures and hyperparameters. So as you go through the notebook, you will find these question marks, 3 question marks in certain places, and your job is simply to replace the question marks with the appropriate code or values to ensure that the notebook runs properly end to end. Okay. Now you can refer back to the lecture notebook. You can refer back to this video if you need to. And here you have it finally. First we'll import the required libraries. We will install the required libraries. Then we will set a project name. This is the project name that will be used at the end. Then we download the CIFAR10 dataset. So just like MNIST, CIFAR10 also is already available in Torch Vision, and how to work with custom datasets. I'll give you a quick hint. There is a type of dataset, there's a type of PyTorch dataset called image folder, and all you need to do is point it to the folder where you have the images downloaded for classification, and it will create a PyTorch dataset for you. For this assignment, you will use the CIFAR10 dataset. So we create the dataset and the test dataset. Then you have to answer some questions. How many images does the training dataset contain? How many images does the test dataset contain? How many output classes does the dataset contain? Can you list the classes? And here's a hint here for you. So for example, if we run this code here, let's answer a few questions. You can see that this time the classes are not numbers. So this time classes do not have numerical labels. So you can just check dataset.classes, and you will see that the dataset.classes contains a list of classes. So what you will get in your tensors, in your labels, you will still get numbers when you create batches of data in your data loader from your dataset. And those numbers will represent, the label numbers will represent the specific indices from the dataset.classes list. Okay. Now, then the question is, what is the shape of the image tensor? So since these are 3 channel images, you can check here that the shape of the image tensor is now no longer 1 by 28, it is 3 by 32. Now to display this image with 3 by 32, you are going to need to permute it. And this was the mistake we made earlier. That's why we got an error, where into permute, you need to give a tuple of values, right? So we did not pass a tuple. And if you do not pass a tuple, if you pass 1 to 0, that's going to cause a problem. So we need to pass a tuple of the new order of dimensions. So we take the image from the dataset, and then we pass it to image.permute. We pass it to the permute method. We get back, we move the channels to the last dimension, and then we call plt.imshow. Now you can see that there is a numeric label that we get back from our dataset. The numeric label is 6, and that corresponds to the 6th element of the dataset.classes, which is frog. And this is an image of a frog. And you can see that this image of a frog, it's really hard to identify even for the human eye. Okay. Then there are more questions. There are some optional questions that you can skip if you don't have the time or are not able to figure it out. And then what you do is you prepare the dataset for training. So you create the training dataset and the validation dataset. And then we create data loaders, and then we visualize a batch of data using the make grid function. So this is exactly what we had done for our MNIST dataset as well. Then we're going to define our model in 2 steps. First, we are going to define this class called image classification base. So just as we have extended nn.Module, we can create our own class which we can then extend, because this whole training step, validation step, and validation epoch end, these functions, we seem to be repeating them over and over. And it seems like for image classification, they are always going to have we are always going to use the cross entropy loss, and we are always going to use accuracy as our evaluation metric. So we are going to create an image classification base class which does not contain the init method or the forward method, but simply contains the training step, validation step, and the validation epoch end and epoch end methods. Okay. Then we will use the same evaluate and fit functions that we had used earlier in our feed-forward neural network. And finally, we will also have the same utilities for moving our data to the GPU. So we have get default device, we have toDevice, and then we have device data loader. And we also have a couple of helper functions, one for plotting the losses and one for plotting the accuracies. So all of these are helper functions that are there for you. And we are also moving all our data to the appropriate devices. Now this is where we come into, your work comes into picture, that now to train the model, what you have to do is you have to extend the image classification base class, and this time inside it you need to define the constructor, the init method, and the forward method. Now in the init method you will define one or more layers. You can create layers like self.linear1, self2, self.linear3, and so on, as many layers as you want, as many hidden layers before an output layer. And then in the forward method you will pass the data progressively step by step through each layer. And all you have to do is make sure that the dimensions line up properly, that the output of the first linear 1 layer can be passed into the second layer, linear 2, and the output of the linear 2 layer can be passed into the third layer, linear 3, and so on. And between each output you have to make sure that you are calling the activation function. So keep that in mind too. So then you define your model, and then you instantiate the model and move it to the appropriate device. Then you evaluate the model, and then you train your model using the fit function. So you train it for a certain number of epochs with a certain learning rate. You can try a different optimizer as well, and then plot the history and plot the accuracies, and then finally evaluate the model. Okay, now you ask yourself, are you happy with the accuracy? If you're happy with it, then you can record the results. So you can now follow through with this. You can record the architecture, the learning rates that you have used, the epochs that you have used, the test accuracy and the test loss and the final accuracy, and you can record all of these things using Jovian.log hyperparams and Jovian.log metrics. So one thing that you're also doing in this assignment is you're going to learn the process of systematically recording each experiment. So once you've defined a model and you've trained it for a certain amount of time and you feel happy with it, then you should record what were the parameters that you used within the model, what were the learning rates you used, what were the number of epochs you trained for, and what was the metrics that you obtained from the model. Okay, and you do that, and then you commit it, and then you continue experimenting. Now you can go back all the way to the training the model section, and then you can try another network architecture with a different set of hyperparameters. Now your goal is to get the highest possible accuracy on the test set. That's what we are going for. And as you train different models, you will see all these values. So you will see that with these hyperparameters, you get these metrics for the accuracy and loss, the final accuracy and loss on the test data set. And you can also include notes about what architecture you have used in the model, or what did you do during training to achieve the required result. Okay, so the goal is to get to the highest possible accuracy on the dataset. Now, once you've done that, we would then, you can then make a submission. So let's see how to make a submission. So you will first have to enter your API key here. So enter your API key from your Jovian profile that is going to upload the notebook to your Jovian account. And then you take this notebook from your Jovian account and come back to the assignment page and paste it here and click submit. That is going to submit the assignment for you. Now, once you're done with that, we will evaluate your assignment. But in the meantime, what you can do next is you can write a blog post. So whatever you have learned till now in the course, or whatever you've learned through a specific technique that you've tried, or through some specific experimentation that you've done, try and write a blog post. And writing a blog post is really the best way to further improve your understanding of deep learning and model training, because it forces you to articulate your thoughts clearly. So here are some ideas for the blog post. Report the results given by different architectures on the CFAR10 dataset. Maybe create a table and write about why you chose certain architectures, write about why you chose certain hyperparameters, and explain what results it gave you. Apply the training pipeline to a different data set, so it doesn't have to be images, it doesn't have to be a classification problem. Improve upon your model from assignment 2 using a feedforward neural network. So feedforward neural networks can be used not only for images, but they can also be used for our tabular data. They can also be used for text data. They can be used for audio. So just look online how to use a PyTorch neural network for audio, for example, or for text, for example, for a linear regression problem or for a tabular data problem. All you need to do is, instead of having a single linear layer, just create a model, a custom model which contains a linear layer followed by an activation followed by another linear layer. Okay, so use it on some other datasets as well. Doesn't have to be just a image dataset. Share some of your strategies, maybe do some research, do some studying, and share your strategies for picking good learning rates, good hyperparameters for deep learning. Present a summary of the different steps involved in training a deep learning model. Now we have covered a lot of material. We've covered how to read in images. We have covered how to convert images to tensors, how to display images, how to create a grid out of images, how to create data loaders which can load the images in batches. We've seen how to move data to the GPU. We've seen how to then create a custom model. Now in the custom model, we've separated out the model specific or problem specific parts as functions within the model, and we've used the generic parts and move them into the fit and evaluate functions. So there is a lot of things that we've covered step by step. So a good way to revise it would be just to present a summary of the different steps involved in training a deep learning model with PyTorch. Another thing that you can do is you can try to implement the same model using a different deep learning library. For example, you can use Keras and present a comparison. So you can see the idea here is not for you to just solve a specific problem, but also really think about what you have learned and consolidate your understanding, and whatever draws your interest, try to write a blog post on that topic. And trust me, you will not regret this part. Even if it may take you about 8 to 10 hours of additional work to come up with a blog post, it will really cement your understanding. And 2 months, 3 months, or 6 months down the line, when you want to revise what you have learned in deep learning, you can quickly come back to your blog post and the notebooks that you have created, and you will be able to quickly get yourself up to speed, especially since you have yourself written that post. Okay, so please do this. It's a great way to improve your understanding. So next we are going to talk about convolutional neural networks, and convolutional neural networks use some other features of images. So they are special neural networks which are somewhat different from what we have looked at so far, and they use something called spatial invariance of images to train better models with fewer parameters. So it's a very interesting upgrade to our model. This time we could get to about 95-96% accuracy. We'll see how to beat that. We are actually going to work with a different data set. Then in lesson 5, we are going to look at ResNets, regularization, and data augmentation. So we are going to take the convolutional neural network and we are going to apply some advanced techniques like adding a residual layer, performing regularization, and doing data augmentation to train a state-of-the-art model within just 5 minutes. So we are going to really see what are some real techniques that practitioners apply while working on real world projects. And then finally in lesson 6, we will turn our attention towards generative networks. So instead of doing classification or regression, we will take everything that we have learned so far in deep learning and we will use that to generate images. So we'll either generate images of handwritten digits or images of anime faces, and there are many other things that you can do with generative adversarial networks. So we will learn about them. And in this process, now today you're doing assignment 3 and you have assignment 1 and 2 to work on as well, and that will set you up for the course project. And the course project is where you will get to apply deep learning on a real world dataset. So let's all gear up for that. Now what you should do next is review the lecture video, run the Jupyter notebook on Colab, complete the assignment, share your work and exchange feedback with others, participate in the forum discussions and join a study group if possible, form a study group with your friends. Now with each of the assignments, you will also find a discussion thread here. So you can just click on the discussion thread and you can ask questions about the assignment and we will help you out. So I will see you in the forums. You can find all the course related information on 0togans.com, and you can follow us on Twitter on @freecodecamp, @JovianML, and I will see you next for lesson 4, convolutional neural networks for images in deep learning with PyTorch 0 to GANs. Goodbye and have a good day or good night.